Hello, Padmakar. Yes. Thank you. Good morning, everyone. We would like to welcome you to the 18th lecture in the Cloud Physics lecture series by IITM. Today we have a distinguished speaker, Dr. Shin-ichiro Shima from Graduate School of Information Sciences, University of Hyogo, Japan. And he will be talking about the Super-Droplet method and its application to mixed phase clouds. We all know that mixed phase clouds are too complex, and so we will be hearing from him about the new developments. And I would like to welcome Dr. Subrata Kumar Das from IITM, or senior scientist from IITM, to introduce him as well as the talk to the audience. Thank you. Subrata, please.
Yeah, thank you, Dr. Tara. So, good morning to all. It's a very privilege to introduce our eminent speaker, Professor Shima. So, Professor Shima is an associate professor at the University of Hyogo, Kobe, Japan since 2011. After completing his PhD in nonlinear dynamics at Kyoto University, he became a research scientist at the Earth Simulator Center, Japan Agency for Marine, Earth Science and Technology. So with an eye on the future of supercomputer, he developed novel numerical algorithms for multi-scale, multi-physics phenomena at this facility and constructed the Super-Droplet method, which is popularly known as SDM method, which is a Lagrangian based algorithm to study the cloud microphysics. Since then, he has been working on this topic to explore the potential of particle-based cloud modeling method. Today, he will be delivering a lecture on the topic Super-Droplet methods and its application to the mixed phase cloud. In this talk, he will describe this method, Super-Droplet method, which is a Lagrangian particle-based algorithm to study the cloud microphysics that requires a lower computational demand than the multi-dimensional beam scale. He will be describing in detail about this numerical method of mixed phase cloud using SDM that explicitly predict ice morphology without making any assumption about ice categories or mass dimension relationship. The performance of this model he has evaluated by conducting a series of 2D large ED simulations of cumulonimbus clouds. In addition, he will also show some of his 3D simulations. With that, I will request Professor Shima to
Let us invite Professor Shima to give his talk. Thank you. Thank you.
Thank you.
Subrata.
Thank you for the introduction. So, yes, hello, namaste, everyone. I'm Shin-ichiro Shima from University of Hyogo. First, I'd like to thank Tara for your kind invitation. It's a huge honor and pleasure to give a talk at this special lecture series. So today I'm going to talk about the Super-Droplet method and its application to mixed phase clouds. So this is today's agenda, and we have 3 parts. And part 1 is for overviewing the Super-Droplet method, SDM in short. And in part 2, I explain how we apply the SDM to mixed phase cloud microphysics, then show you several series of 2D simulation of a cumulonimbus for model evaluation. And in part 3, I will show you the first preliminary results of 3D simulation of the same cumulonimbus using our model. So let me switch to part 1 of my talk. Okay, so part one, overview of the Super-Droplet method. So STM is a particle-based scheme to simulate cloud microphysics accurately. And in this part of my talk, I will explain the present and the future of GSTM and Lagrangian particle-based cloud modeling approach in general. First, okay, let me turn on the pointer. Yes, first I'll explain very briefly what's happening in the clouds. Then explain my thoughts why it is still difficult to simulate clouds. And I prepared section 3 to explain the basic equations of clouds, the structure of the basic equations of the clouds. But I noticed that it takes too much time. So I just explain the most important point and move on to the next section. And here I will explain the basic idea and the characteristics of the GSTM and comparison to other models. And finally, in this part, I will show you several example simulations of STM for model evaluation. Not evaluation, just demonstration of STM. Okay, so first, what's happening in the clouds? So we have tremendous number of aerosol particles in the atmosphere. Some of them act as condensation nuclei and create cloud droplets. They grow by condensation and eventually by collision coalescence and become rain droplets. And these rain droplets fall down to the surface. But most of these cloud droplets evaporate and become aerosol particles again. This is called cloud aerosol interaction. This is basically what's happening in warm clouds. But when it comes to mixed phase clouds, the microphysics is very complicated. More complicated, I would say. So first, we have various ice nucleation pathways. So we have homogeneous freezing, condensation freezing, and immersion freezing, and these must be the dominant mechanism. But other than that, there are several mechanisms being proposed and still being actively studied. In addition to freezing, we also have melting, deposition, sublimation, riming, aggregation, breakup, and so on. Through these processes, ice particles exhibit diverse morphologies. Some are very needle-like, columnar, plate-like, dendritic, and some rimed, and some create some aggregates. So why is it difficult, still difficult to simulate clouds? I think there are several reasons. So one is the uncertainty in the initial and boundary condition. We also have a problem of the grid size. In particular, for weather prediction, it is still difficult to use sufficiently small grid size to resolve convective motion of the atmosphere due to the limitation of the computational power. The third reason would be the lack of basic understanding in cloud microphysics. And fourth would be the lack of numerical schemes suitable for cloud microphysics. Here I say that there is a lack of basic understanding in cloud microphysics, but at the same time, we do know, to some extent, we know a lot about cloud microphysics. We have a lot of knowledges, but however, these knowledges are not properly incorporated into the current generation of cloud models. So this is primarily what STM is aiming to resolve. So here I have some supplemental slides. This slide showing the impact of the grid size. So if you compare these two panels, one with a simulation of a storm with 150-meter grid size and 40-kilometer grid size, we can clearly see the difference. The above simulation looks very realistic and reliable. This shows the impact of the cloud microphysics model. So this is a simulation of a scroll line. And yes, here we can see the result is very sensitive to cloud microphysics model. So if we just change the cloud microphysics model, then we can see the result changes very much. I would also like to mention that cloud aerosol interaction is still an open problem. It is still the largest uncertainty for climate change evaluation. This is a figure from the 5th assessment report by IPCC, and this is 6th assessment report recently published. We can see still the uncertainty is very big. So now let me move on to section 3, and here I was thinking of explaining the structure of the basic equations of clouds. But let me just explain the most important point. First, there is a hierarchy of description of cloud microphysics. STM and other particle-based schemes are basically for this level of description, particle dynamics with stochastic collision. So here we are assuming that the collision of particles occurs in a stochastic way, not in a deterministic way. In that sense, this is not the most microscopic fundamental level of description. We have some approximation here. In that sense, I would like to call this kinetic description. To simulate cloud microphysics accurately, we can consider predicting the behavior of all the real particles. But practically it's impossible. So we consider much smaller number of sample particles of this real droplet or real particle population and follow or predict the behavior of these sample particles instead, using elementary process level equations. So this is basically what we are doing in STM and particle-based schemes. So let me skip this part. So Superdroplet is the name of the sample or computational particle, which represent multiple number of real particles. To make it computationally efficient, we developed an original Monte Carlo scheme for coalescence. And as a result, it's suitable for simulating detailed cloud microphysics. And we developed it basically for cloud microphysics, but we can apply it to any systems in which particles collide and coalesce repeatedly, like planet formation, spray combustion, bubbles, volcanic films, population dynamics, and so on. This figure illustrates the conceptual difference between STM or other particle-based schemes and other cloud microphysics models. So this is a scatter plot of real droplets in droplet size, CCN size space. So we approximate the population of these real droplets by much smaller number of weighted samples. These samples are called superdroplets or superparticles, depending on what they represent. In bin schemes, they approximate the population of real droplets by a histogram. In this case, we need a two-dimensional histogram. But due to the computational cost, most bin schemes approximate this by a one-dimensional histogram, discarding some information about CCN size. In bulk models, they do not predict droplet size distribution. They assume that their droplet size distribution is well approximated by a simple function and just predict their statistical properties like mass, number, and so on. So this is a basic difference. So we are arguing that there are three issues of bin schemes and that all these issues can be resolved or at least relaxed if we use STM or similar particle-based schemes. The first issue is the numerical diffusion. We have numerical diffusion in bin schemes because they are based on Eulerian representation. But we do not have numerical diffusion in STM because it's based on Lagrangian representation. The second issue is a curse of dimensionality. That is to say, the computational cost of bin schemes can increase very rapidly if we consider more particle properties. We call this attributes, particle attributes, like particle temperature, electric charge, chemical species, ice particle shape, and so on. In that case, we need to add more axes to this attribute space. And in that case, the histogram will be high dimensional. So it's very difficult to calculate the time evolution of the histogram. The third issue is this would be more subtle compared to the above two issues, but it's on the breakdown of the Markovsky equation. Markovsky equation is a basic equation that bin schemes are solving. So we call this Markovsky equation, but in microphysics community, we also call it stochastic coalescence equation. It looks like something like this. It's a time evolution equation of the number density of particles, n. So we have the advection term in real space and attribute space and collision coalescence integral term. This is the basic equation bin schemes are solving, but in some situations, the discreteness of particles become evident, and Markovsky equation becomes not valid. In that case, we cannot use bin schemes, but STM is free from this problem, in short. Let me skip this part, explaining bulk scheme and comparison to other particle-based scheme. in cloud microphysics area and other research areas. Okay, let's move on to section 6. So what can STM and other particle-based schemes in general be used for? So we already have many studies using this framework to warm clouds, and some already started using this framework to study aerosol processing and aqueous surface chemistry. Application of this framework to ice or mixed phase clouds is advancing relatively slowly, but we already have several types of models using this framework. And we recently developed a model that explicitly predicts the morphology of ice particles. And this is the main focus of part two of my talk today. Another direction is to use this framework for modeling subgrid scale turbulence, in particular the supersaturation fluctuation. Now let me show you several example simulations of STM for demonstration. This is the numerical simulation of 2D. This is in 2D, but of a shallow cumulus, maritime shallow cumulus. I conducted this simulation almost 17 years ago as a proof of concept of the idea of STM. So this is the sea surface, and we have humid air stratified. The updraft is initiated by a warm bubble placed in the middle of the domain. Then it creates a cloud, cumulus cloud. Then it precipitates and finally disappears. So if you look closer, you can see the cloud and the rain. Okay, once again, consists of very small points, and these are super droplets. And actually, everywhere in this domain, we have super droplets. So even in these black regions, we have super droplets moving around. They are representing aerosol particles. So we couple the STM simulation with LES simulation to do this simulation, to simulate the behavior of clouds. Snapshot. This is a 3D simulation of the same setup. So again, I conducted this simulation 15 years ago, and at that time I needed to use one of the most powerful supercomputers of the world, JAS simulator, and to finish this simulation, relatively small, shallow cumulus simulation for 30 minutes, I needed to spend about 1 week of JAS simulator. But these days, I think a small cluster machine, maybe not very small, but relatively small cluster machine would be sufficient for this simulation. Because it's 3D, we can see the shape of the cloud looks more natural. They do not stretch horizontally too much. I hope you can see this clearly on your screen. Okay, next, this is a snapshot. Now we are using this model, our model for the simulation of marine stratocumulus. And this is a result of using DICOMS to RF02 setup specified in Ackermann et al. 2009. And here we can see after the spin-up period, the creation of the stratocumulus deck and the drizzle from it. They are being simulated in a realistic way. Again, this is a snapshot. Yes. And this is a horizontal distribution of the stratocumulus being simulated. So after the spin-up period, we can see the creation of closed cell-like structure naturally. Let's move on to the next example. This is a simulation of an isolated cumulus congestus based on SCAMS campaign. So this simulation and visualization were done by my collaborator Toshiki Matsushima. And this movie is uploaded on YouTube. You can watch it from here. So let me show you this. Wait a moment. So this is a 3D movie. You can change the direction as you like. So if you have a virtual reality goggle, then you can watch it in 3D. Please try it. You have one. So initially, we have a very small chunk of cumuli clouds, but after that, we change the surface flux condition and create this cumulus congestus. So it's much bigger than the first small shallow cumulus cloud. This congestus cloud developed up to like 6 kilometers. And you can see the entrainment between the air, ambient air, is very realistically reproduced. Maybe once again. Let me also mention that the coarse grid resolution version of this case was used for the previous ICMW 2021 case study. So we conducted a model into comparison project based on this setup. Okay, so this is a 2D result of 2D simulation of the cumulonimbus case, but I will explain this later, so let me skip. So that's it for the first part. So I explained the basic concept of STM and showed you various examples of STM. Any questions up to now, or should I move forward?
Yeah, please move forward. We can have the questions at the end.
Okay. So let's move on to part 2. So wait a moment, where is it? Okay, part 2 is for the application of the Superdroplet method to mixed phase cloud microphysics and 2D simulation of a cumulonimbus for model evaluation. This is a collaboration work with Yosuke Sato and Akihiro Hashimoto, Ryohei Misumi. So basically, this part 2 is a summary of our paper published on GMT 2020. Here we applied STM to mixed phase cloud microphysics and constructed a model that explicitly predicts the ice particle morphologies. And we conducted a 2D LEA simulation of a cumulonimbus for model evaluation. So we have a lot of slides here because it's a long paper, but I don't go into the detail. If you're interested in, please read the paper. And today I just explain the basic strategy, how we apply CSTM, and skip 3, explaining the state variables we consider, and move on to 4, the time evolution equations. Let me explain. Okay, this is another long section, but let me explain briefly what sort of equations we are solving in this model. I'd like to show you that our model is actually based on process level equations. Then some detail about the numerical schemes implementations in section 5, but let me skip and let me show you the result of the 2D simulation. Okay, this is my plan. And so let me skip this part. And actually, this I already explained. So let me explain the basic strategy, how to apply GSTM. So to express the shape of ice particles, we cannot, of course, express the complicated shape of ice particles as is. We need some approximation. So we approximate each ice particle by a polar spheroid, following Chen and 1994 for the approach. So we will add equatorial radius, polar radius, and apparent density rho to the list of attributes, so particle properties. In addition to these 3 new attributes, we also track the line mass and number of monomers in each ice particle. So we also consider this is the attributes of this new model. But note that we do not use this information for time evolution in the current version of our model. But I'm sure we can use this information to refine, sophisticate our model. So this is a representation of ice particles. And regarding ice nuclei, we introduced freezing temperature attribute based on inner theory. And this can account for homogeneous and condensation, immersion, freezing. This is a list of cloud microphysics processes considered in our model. In addition to the warm cloud microphysics processes, we consider that, of course, the terminal velocity of ice particles and ice particle formation through homogeneous and condensation, immersion, freezing, melting, deposition, sublimation, droplet ice collision riming, and ice-ice collision aggregation. These are considered in our model. And here, let me excuse that collisional or spontaneous breakup processes of various kinds listed below, in particular important for mixed phase clouds. But any of these are considered in our model yet. This is our future work. So this is a basic strategy, and let me skip explaining the variables. Let me briefly explain the time evolution equations we are solving in our model. So as I said, our model is based on kinetic description. So we need process level equations to construct the model. So for the droplet terminal velocity, we are using Bayer's formula, 1976. And for ice particle terminal velocity, we are using Bohm's formula. And to do so, we need to evaluate the actual area size of particle perpendicular to the fall direction. And we derived some simple formula to evaluate it, and using Bohm's formula. And here is some detail about Bohm's formula, but I don't go into the detail. And it's good that his formula can be applied to relatively high particle Reynolds number. Regarding immersion, condensation, and homogeneous freezing, as I said, we introduced freezing temperature attribute. So here we employed singular hypothesis and ignores the time dependence of freezing. So we consider that droplet I freezes immediately when the ambient water vapor is supersaturated over liquid water and the ambient temperature is lower than the freezing temperature of the particle. And so this is a kind of freezing temperature is a particle specific property, and we can determine this by inner theory by using some inner density formula. For example, for mineral dust particles, we can use the inner density formula of Niemann et al. In 2012, and this is a corresponding freezing temperature probability density. So the horizontal axis represents a freezing temperature, and this is a probability density. So we can see if the mineral dust diameter increases, it tends to freeze at higher temperature. And we draw a random number and determine the each particle specific freezing temperature. And we consider that melting occurs immediately when the temperature is above 0 degrees Celsius. For condensation and evaporation, we of course use Taylor curve and consider the impact effect of curvature and dissolution. So it means here we are also explicitly considering the activation and deactivation of CCN particles. And regarding deposition and sublimation, we consider primary and secondary growth habit through using Chen and Lam 1994 formula model with various modifications. And here it is known that ice crystal growth, depositional growth, has a strong dependence on temperature, and this is called primary habit, and to lesser extent on supersaturation, secondary habit. And we use inherent growth ratio function. The primary habit is kind of considered through this inherent growth ratio function. So this is a function of temperature, and Chen and Lam created this by fitting a laboratory measurement data. Yes, and we are also using this. So, and the secondary habit is, yes, being considered through the raw deposition formula, the deposition density formula Chen and Lam proposed. So, yes, it depends on the gamma, inherent growth ratio, and the supersaturation. Anyway, these two habits are considered in our model. Regarding coalescence between two droplets, we need to specify the collection efficiency. And we are using collection efficiency proposed in C-Selberg et al. 1996, and which is actually a compilation of various previous studies. For rhyming, again, we need to specify the collision rhyming collection efficiency, and we combine the formulas of Baird and Grove 1974 and Elfani and Mitchell 2017. Yes. Regarding rhyming, we need to specify how to calculate the outcome of rhyming. And here we employ filling in simplification and preserve the maximum dimension. And regarding aggregation between two ice particles, again, we need to specify the collision aggregation correction efficiency, and here we assume it's a fixed constant 0.1 following Morrison and Grabowski 2012 and Field et al. 2006. And I'm sure this is a simplification, and yes, we have to improve this in the future. But for now, we are using this constant value for the collection efficiency. And for the outcome of aggregation, yes, this is another complicated point. Chen and Lam already proposed some, procedure, how to calculate this, but it seems it's not working nicely. In some situations, it produces two light ice particles, lighter than the air, so it's unphysical. So instead we developed an intuitive model to fix this. The basic idea is to consider the compaction of aggregate through restructuring. So we consider that if the ice particle is very fluffy, has a very low density, we consider that it should change their shape and become dense. So with this, we avoid the creation of very light ice particles, in short. And I think that's it. Yes, that's it for the basic equations. So we are solving these equations for each superparticle. So let me skip some detail about the numerical scheme and implementation. Let me show you the result of our cumulonimbus simulation in 2D. So this is the setup of the control ensemble. So the sounding of Kane et al. 2004 is used. And for aerosol particles, we consider that there are two species, one composed of pure ammonium bisulfate and the other composed of mineral dust internally mixed with ammonium bisulfate. And this is a grid size superparticle number concentration, initial superparticle number concentration and time steps being used for the control ensemble. And after the control case, we conducted a series of simulations changing these grid size superparticle number and time steps to assess the numerical convergence characteristics. So first, let me show you the behavior of the control ensemble. So before that, let me explain how we categorized hydrometeor particles. So let me emphasize that we are not using ice categories in our model. This is a salient feature, one of the salient features of our STM model. We treat ice particles in a unified way. We do not use categories. But when we interpret and analyze the result, obviously it's useful, convenient to categorize ice particles. So this is a criteria how we did this. So if ice particle contains, if the line mass ratio is larger than 0.3, we consider it's a global particle. And if the size is big enough, larger than, I don't remember, 2 or 4 millimeters in diameter, then we consider it's a hailstone. Anyway, yes, this is a criteria of global or hail. And if it is not a global but has monomers more than 10, monomer means primary ice particle, then we consider it's a snow aggregate. Otherwise, we consider it's a cloud ice particle. This is a criteria. So let me show you the result. So this is the time evolution of water pass and precipitation, surface precipitation. And the solid line represents the typical representation, typical behavior of the control ensemble, defined as the member that produced precipitation closest to the mean here. And I will show you the time evolution of the typical realization here. So the color represents the hydrometeor type. White corresponds to cloud water, yellow corresponds to rain droplets, rainwater, and blue for cloud ice, red for global or hail, and green for snow aggregate. Okay, it looks good. So let me show you several snapshots. So this is a snapshot from the towering stage. So at this moment, we can see the cloud is composed mostly of cloud droplets, white. But at the same time, we can see the start of the creation of rain droplet and ice particles. These rain droplets are created through collision coalescence of supercooled cloud droplets. So it's still a warm process. But soon after this, in 100 seconds, 1 or 2 minutes, we can see the rapid creation of the red particles, global hail particles here. This is, of course, happening through the rhyming between ice particles and supercooled liquid water. And this is a snapshot from the mature stage of the cumulonimbus. We can see a lot of surface precipitation and also see the start of the creation of an ambient cloud. This is from the dissipating stage of the cumulonimbus. Here we can see that supercooled liquid water still exists in upper part of the cloud, just below the homogeneous freezing level, still at this stage. And I found this interesting. And finally, yes, this disappears, but not disappear, but yes, slowly becomes stable and the Yambu cloud stretches. Okay, so with this, I would like to conclude that the typical life cycle of a cumulonimbus was well reproduced by our model. Now I would like to assess, evaluate the ice particle morphologies. So we compare the mass and velocity dimension relationships with existing formulas. So the left panel corresponds to the mass dimension relationship, and right corresponds to terminal velocity dimension relationships. And the colored shades corresponds to our model, and the colored lines corresponds to the existing formulas based on measurements and theory. And I would say the result agrees fairly well with existing formulas, because the red shade is located closer to the red lines, and green to the green lines, and blue to the blue lines. And this is a snapshot from the towering stage, mature stage, and dissipating stage. Okay, that's it for the control case. And after that, we investigated the numerical convergence characteristics. And I'd like to go through this very quickly, but here I'm showing you how the domain average precipitation and the water path, maximum value of the water path changes as we increase the superparticle number concentration. So the domain average precipitation is not very sensitive to the superparticle number concentration, but we can see the water path changes as superparticle number concentration increases. And from this, I concluded that somewhere around here seems to be enough. So we concluded that about 100 superparticles per cell seems to be sufficient for an accurate simulation. By the maximum of water path means the maximum value of this curve. So for cloud water, this is the maximum value, and global, this is the maximum value. And I plotted the maximum value for each case, and calculated the mean and standard deviation here. Okay, in the same way, we assess the grid convergence, and our conclusion is that about 60 meter grid resolution seems to be sufficient for good grid convergence. Regarding the time step, it seems it's relatively insensitive. The result is relatively insensitive. It for the second part, and let me move on to the third part, the 3D result. But I don't have that much to show you here, so I think I'm almost done. Where is it? Yes, part 3, 3D results. So let me skip these. Nice. So for the 2D case, yes, we confirmed that our model successfully reproduced a typical life cycle over cumulonimbus, and the mass and velocity dimension relationships looks okay. And we also confirmed the numerical convergence characteristics. And after that, we conducted another study still using the 2D setup. This is a collaboration work with Reiji Yamada, and this is from his bachelor's thesis 2020. And here we changed the aerosol number, hygroscopic aerosol number concentration from 1 to some 1,000, and we found that precipitation peaked at around Na equal to about 25 per cc. And we also confirmed this is due to the warm phase invigoration. I mean, the increase of precipitation at low Na is due to the warm phase invigoration. With this in our mind, let me show you the 3D results. So, okay, this is a parameter I checked for this study. So for hygroscopic aerosol particles, I tried 3 different number concentration of Na, 100, 300, and about 900. And this time I also tested changing the mineral dust diameter. So up to now, I only assume that it's 1 micron in size, but this time I tested 0.1 and 10 microns as well, and also changed the grid size. By the way, remember that if we increase the mineral dust size, larger dust tends to freeze at higher temperature, as the probability density suggests. This is some detail about the numerical setup. I'd like to skip here. I don't go into the detail, but let me just mention that the domain size is 60 kilometers times 60 kilometers times 20 kilometers. So now we are able to conduct this size of simulation with reasonable amount of computational resources. So let me show you the result. So here I have the grid convergence analysis, but okay, it's not very, very interesting. So let me just explain the key conclusions. So, okay, from the accumulated precipitation amount, it seems 100 meter grid size seems to be sufficient. 200 seems to be too big, but 100 seems to be sufficient. So it seems it's slightly better than the 2D case. And the result seems to be sensitive to the hygroscopic aerosol number concentration, but less sensitive to the mineral dust diameter. We can see it from okay, it's not easy to see, but if we check the difference here and here, and here we can see the precipitation amount is almost the same for different mineral dust diameter. This is a key finding here, and let me show you finally the result of the highest resolution case. So in this slide, we fix the mineral dust diameter size to 0.1 microns, and comparing the results with different value of Na, 100 per cc, 300 per cc and 900 per cc. And here we can see for lower value of Na, the creation of Graupel and Hale particles are enhanced. But for higher number of Na, the creation of Graupel and Hale particles are suppressed, and instead the creation of snow aggregate is, the time evolution is a little slower but enhanced. And I think this is a kind of reasonable result, because if the number concentration of Na is small, it means that cloud droplet size is big, so it tends to rhyme with existing ice particles. And from here we can see the impact of the mineral dust is small. This is for mineral dust size equal to 1 micron, and you can see the behavior looks very similar compared to the previous one. And this is for D dust equal to 10 microns, and the same, looks similar. So sorry, I should have mentioned that this is these are results from the 3D simulation, but I'm showing you the vertical cross section in the middle of the cloud, so you cannot tell if this is 3D or not. But actually, this is from a 3D simulation. so yes. It's different from the previous 2D case. And finally, let me show you the time evolution of the ice particle morphologies. Is it? So the horizontal axis corresponds to the mineral dust size, and vertical to the number concentration of hygroscopic aerosol particles. Again, from here, the impact of Na is big, but the impact of E dust is relatively small. They all look similar. Once again. Okay, that's it. And this is the first preliminary result of our 3D simulation. And so this is the end of my talk. And to summarize, today I overviewed the Superdroplet method and explained how we applied STM to mixed phase cloud microphysics, and showed you the 2D and 3D simulation of cumulonimbus. So I hope that from my talk today, you are convinced that the STM and other particle-based models can connect aerosol scale and cloud scale seamlessly from the process level. And I think this encourages us a lot to have more tight collaboration among lab experiments, field measurements, and cloud modeling. Okay, that's it. Thank you so much for your attention, and I'd like to take some questions.
Thank you very much, Shima. And Mahin, let us take questions from the YouTube first, if there is some.
Yeah, YouTube, we don't see any questions. So I think till any question, if any comes, then we can discuss among ourselves. I mean, our panelists can put their questions.
Yeah, then it is open to the panelists to. Please go ahead, Subrata, you were asking something. Hello? Mahin?
Yeah, Subrato, you have any question?
Yeah, means this was very interesting talk. So means I was just wondering this mixed phase, whatever you are talking about, whether there are something like different processes like means like collisions or breakup kind of the thing, whether that will also have some kind of impact.
Yes, of course. So first of all, let me show you the list of processes being involved in mixed phase class. Where is it? Yes, here it is. Can you see my screen?
Yes.
Yeah, we can see.
Okay. So yes, we have various processes and related to collision. We have three types of how to say collision aggregation process. So we call coalescence if it's a collision aggregation between two droplets, and if it's a collision between droplet and ice, we call this collision liming, and if it's an aggregation of ice, it's just aggregation. So we are considering these three processes, and yes, these are playing a very important role in this phenomenon. So I think you saw the development of red shaded area. These areas represent the global and hail particle regions, and this is being created mainly through this droplet ice collision liming. So it's very important. But regarding breakup, as I said, it's we have various types of breakup processes in this phenomenon, and it's important in particular for mixed phase clouds. But none of these are considered, at least in my model. In some other particle-based model, it's already being considered, but not in our model yet. And I think yes, it's important. It changes the behavior very much, like the rain droplets distribution, creation of the cold pool, and also the number of ice particles here and there. It has a very big impact. But yes, this is future work.
Yeah, so then how about the vertical velocity? It means whether there will be like a updraft kind of region and
Yes, of course, it depends on the location, and because this is a cumulonimbus cloud, the updraft is relatively strong. And in the 2D case, I actually measure the maximum vertical velocity during the simulation, and I don't remember the exact number, but it's like 40 meters per second or something.
okay. So this dominating process will be for which one? Means like if your updraft is like higher, then which one will be more dominating?
It's a very difficult question. I cannot say which is dominating the behavior. All of these processes are kind of equally important. We need to consider all of these to explain the phenomena. Yes, none of these can be ignored, I think. And I think breakup has to be considered.
Okay.
Are there any questions further, Mahen?
Yeah, there are no questions. Yeah, you can also, yeah.
I like to ask a couple of questions to keep the discussion going. Since it is relating to the vertical velocities, I thought, Shima, are you able to hear me clearly?
Yep, I can hear you.
You are indeed assuming a warm bubble in your simulation to trigger the convection. So how do you think the realistic initialization might have an impact in your simulation? Because what I have noticed is your clouds are indeed triggered very quickly, and they go into mixed phase within few seconds. So how are you going to consider this warm bubble or the more realistic initiation of the convection?
Very good point. Yes. So, okay, let me show you the result for the warm clouds. So, where is it? Not this one. In part 1 of my talk, I showed you 2 examples of convex cloud. One is a shallow cumulus case, this one, and the other is cumulus congestus case, this one. And okay, as you said, I initiated the updraft convection by a warm bubble for this case. So as you may have noticed, the initial shape, the shape of the cloud in the initial phase is very smooth and not like a real cloud, because we do not have any turbulence in the atmosphere, and it's kind of forced to be created by a warm bubble. So it's very unnatural. But for this case, we are very careful about this point. So, okay, let me show you the movie once again. So before creating this cumulus congestus cloud, we have a 1 hour spin-off period and created a natural boundary layer turbulence condition. Then after this spin-off period, we changed the surface flux, not a warm bubble, but the surface flux, and that started creating the cumulus congestus cloud in the middle. So in this case, from the very beginning, the shape of the cloud looks very natural, because the atmosphere around it is already to some extent turbulent and natural. So this makes this difference.
Yeah.
So
so this in this particular example, you have used the surface fluxes indeed for initially you started with a bubble, then you made no, maybe initially also you started with surface fluxes, because otherwise it may be unnatural again. So you got several cumulus forming, and then they have dissipated. Many of those cumulus have dissipated. What I see is that there is a conjectors forming, and only conjectors is there. So is it so that the cumulus also, the dissipation of the cumulus also contributed in addition to the surface fluxes?
Yes, it's due to the surface flux we imposed. So okay, let me go back to the movie once again.
Yeah,
so,
it's a very interesting case where one deep convection is forming, and from it is typical of a continental boundary layer where shallow convection initiates, and then it is forming a deep convection or a conjectors cloud. So I think it really makes a real case study for intercomparing with observations, as well as to see what processes are being important in deepening these clouds.
Yes, regarding the dissipation of these small
dissipation of the small one or the surface fluxes. What exactly is playing a major role in that conjectures?
So in this specific case, we kind of change the surface flux condition and kind of switched off the uniform surface flux and turned on a Gaussian weighted surface flux weighted the middle of the plane. So we do not have any surface flux anymore in the outside of the cumulus congestus. That's the reason why we do not see any cumuli anymore after the spin-off period.
Okay. Yeah, I think there are some more questions now.
Yeah, there are a couple of questions in the YouTube. Dr. Abida Chodori, she's asking, she's at first complimenting you, Dr. Shima, for the informative talk. Then her question is, do you think the use of ensemble of models for initial condition or boundary condition is an option which can improve the simulation result? Dr. Shima?
Models for initial condition or boundary condition. Ensemble.
Maybe her question is regarding how you initialize the model with the sounding with a different sounding, or then you are indeed using the periodic boundary condition, right? Or maybe if you change the boundary condition, will your results be different?
That's right. So yes, this system is very sensitive and chaotic. So yes, that's right. We need to be careful about the initial condition, side boundary condition, and also surface boundary condition. So we need to be careful how they are affecting the results. We don't know the very kind of accurate surface flux or accurate initial condition. So we need to do some ensemble simulation for better comparison with observation. That's right. But it takes a relatively big computational resources to run this simulation. So we cannot run like 100 ensemble member or 1,000. So we have to be very careful how to design our model into comparison, not model, but comparison with observations. But you are right, we have to be careful about this point. And yes, I will think of it more now, because yes, as I said, now I think we are ready to do some more detailed comparison between measurement, observation, and model. So yes, I keep this in my mind. Thank you for your comment.
Yeah, thank you. There is another comment from Neelam Malap. She's asking, how about the effect of surface fluxes on the three-dimensional simulation? That will affect the surface precipitation?
Good point. So regarding the cumulonimbus case, yes, this time we didn't use warm bubble, but yes, we triggers the cumulonimbus by a surface flux. But yes, the size or the rate of the surface flux is something arbitrary. We just followed not exactly the same, but follow what Professor Kane did in their 2004 paper. And I don't know how realistic it is. So we should try changing the area size and the heating rate and so on. And of course, the area size would change the result very much. And also we need to impose some spin-up period to kind of create natural turbulence before the cumulonimbus triggered, but the profile is very unstable. So I think small perturbation can create a big cumulonimbus in this case. So it's not as easy as you may think compared to the cumulus congestus case on the YouTube. But yeah, yes, you are right. We have to be careful about this point as well. And I think it has a big impact.
Are there more questions, Mohin?
Yeah, there are no more questions. Yeah. So any of
you
the
have
panelists,
some question or anybody else?
No, I don't have, but yeah, I just have a point here. Dr. Shima, have you ever compared your simulation with any, say, radar, dual polarized radar data, so that your mixed phase precipitation, say, type of hydrometeors are being compared with your simulation? Any case study?
Not yet. Yes.
Not yet. Okay. Yeah.
I'm doing such kind of comparison and yes, look forward to the result, but not yet. Yes. As I said, this is the first preliminary result.
Okay. Yeah. Thank you. Yeah.
Mahin, I have a couple of other questions also, just for a further understanding. See, Shima, you have considered the cloud droplets as radius less than 40 microns. So actually, what happens is in the in situ measurements, when we have a droplet measurements, droplet probe, for example, we have up to 50 microns diameter. When you want to intercompare with observations, it will be a little bit complex there. I just want to, that is something that I want to point out. Then another point I want to ask is regarding the mass dimensional relationships. You have shown throughout your simulations, means intercomparison with your simulation and the literature, established relationships from the literature. But it is noted that during the initial part and even the middle of your simulation also, there is a significant deviation from the literature. However, your results are matching very well with the dissipation stage of the cloud. So do you have any comment on that? This is a consistent behavior I have seen with all the results that you have shown. Yeah.
Okay, first from the cloud droplet definition, size.
Size spectrum. It is just a comment that if you want to make an intercomparison with the in situ measurements, that will need to be considered. So
yeah. For example, CDP provides from 2 to 50 micron.
Around 40 micron, it is very uncertain because we are actually bringing two different probes and stitching the size distribution together, CDP and SIP, or maybe 2DS, or maybe 2DS can give little better, but the point there is bit more uncertainty will be there when you compare with observations there.
Okay, the answer is very clear. So this criteria is used only for the post-analysis. We do not use this criteria.
So you have the control on that, right?
Yes, and this doesn't affect the result. I mean the simulation. Yes, this is just for post-analysis. During the simulation, we do not distinguish cloud droplet and rain droplet. So not a problem. Yes, and that's simple.
So always you will be saving the particle by particle data, or?
Yes. So yes, okay, but I have to be careful how to save the data. But during the simulation, anyway, we do not distinguish these cloud droplets and rain droplets. And regarding the mass dimension relationship. Yes, I don't know how to evaluate this accurately, but
yeah,
yes,
it's a very interesting result, and the way it is behaving very close with the previous literature. It is during the later part of the storm, I think.
So it looks similar. It's good, but yes.
Yeah, definitely it looks similar, but there is more spread in the initial stages. Maybe it is something to do with the type of hydrometeor, or I don't know what exactly.
So first, we have to be careful how accurate those formulas are. I'm using this for reference, but it's not everything. Of course, they are so this is indeed from various observational data and from various literature, and this is a combination of this figure is a combination of the formula. So I don't know how well these lines cover what's happening in reality. So this is first point. And yes, I think there has to be many points in our model that has to be improved. But I don't know how we can tell this point is strange or not. Okay, in my GMD paper, I initially observed much strange shape ice particles, like they are located somewhere around here or here, and I kind of fix these problems one by one by checking what's happening, what was happened to these strange ice particles, and fix the basic equations, the process level equations, to make it right. Please see my GMD paper. So we can do some that to fix the model, and we can do something like that. But to do so, we have to specify particle looks strange or not. But from this figure, I don't know how to tell this figure is not correct or not. we see some deviation, but I don't know if it's strange or not.
Thank you for giving that insight. I had one more question regarding your mineral dust simulation. Actually, when you increase the number concentration, it is noticed that there are more supercooled liquid in the initial stage of the storm, and which is indeed changing the ice hydrometeors or mixed phase significantly. Did you make any specific analysis of the supercooled liquid? And I did not see where the freezing level is in this. I suppose it is around 4.5 kilometers. Yeah, so but in the initial stage of the cloud, and that is something that I've noticed, and also there appears to be some cloud lifetime impact in the polluted simulation, that cloud was staying longer time, so the stratiform cloud. So these comments I noticed these behaviors.
Thank you. So yes, I just got this result, so I'm wondering how I can analyze this. Thank you for your comment.
Very nice. Thank you so much for accepting our invitation. And Mahina, are there any further questions?
No, there are no more questions. Yeah.
And we are wanting to thank you profusely, and it is really an honor for all of us to have you here and to talk in this lecture series. And it appears, Bipin, do you have any question?
No, I was listening nicely. It was very good talk. And thank you very much for Professor Shima, who have given the time to us. And we are actually listening him, at least in IIT, we are listening after 4 years. No? He gave a talk in 2018.
Yeah.
August.
Thank you. Thank you very so much.
Look forward, look forward that he should visit again to IITM and interact with the students and the scientists there.
Yeah. Thank you so much. And I think we can now close. If there are no further questions and nobody wants to have any further discussions, then maybe we can close.
Thank you, Dr. Shima, for your nice talk.
Thank you.